Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program.
Okay, cosmic rays. All of our information about the universe comes in the form of electromagnetic radiation, that is, light, infrared, ultraviolet, radio signals, X-rays, and so on. But there is another flux reaching our Earth from space, energetic nuclear particles called cosmic rays. Just as a brief outline, I'd like to start with some simple definitions, just to make sure you all have the background appropriate. Talk about the history, the discovery of cosmic rays, a few words about detectors, and then I'd like to break the cosmic ray spectrum into three energy regions: the low, middle energy, and the very high energy. And in the latter part, I'll be using information from the very recent experiments of the Auger collaboration, which I'll tell you about later. Okay, a few years ago, it's interesting, the American Physical Society decided to form a new division in this area of physics. There are other divisions in the American Physical Society, a division of nuclear physics, high energy physics, or elementary particle physics, I guess, and atomic, molecular, and optical physics, and so on. Well, the first idea was to call this a division of cosmic ray physics, but people objected. They thought, oh, that's kind of an out-of-date term, so it seems, so instead it's called the division of astrophysics. And, okay, this area of science is usually in contemporary discussions referred to as astroparticle physics or particle astrophysics, or simply just astrophysics. Well, anyhow, first, a little introduction, just to remind you, we'll be dealing with very, very large and very, very small numbers. We'll use exponents of 10 to represent the large and small numbers. For example, 10 squared is 100, 10 to the minus 3 is 1 over 1,000. And then we have these prefixes: million, billion, trillion, and quadrillion, and so on. Mega, giga. Interesting that the word billion, it is an English term. In European countries, biard means a trillion. So the term giga, or the prefix giga, gia, the letter G, rather than B, came to be more universally adopted for 10 to the 9th. Anyhow, units of energy and mass, just to note the meter, kilogram, second system of units, which is universal in modern physics. The unit of energy is the joule, mass, the kilogram, distance, meters, and seconds for time, of course. And a watt is 1 joule per second. A kilogram is about 2.2 pounds, and electrically, the unit of charge is a coulomb, electrical potential is a volt, and a 100-watt light bulb is what you get with an ampere flowing through a potential of about 100 volts. Anyhow, elementary particles, the proton, the electron, mass of a proton is about 1.67 times 10 to the minus 27th kilograms. And its electric charge is 1.6 times 10 to the minus 19th coulombs. So it's a very, very tiny thing. The electron mass is even smaller, 10 to the minus 9 times 10 to the minus 31st. A convenient unit of energy is the electron volt. That is, the energy an electron would have, kinetic energy, accelerated through a potential difference of 1 volt. And, of course, in view of the electric charge of an electron, that's only 1.6 times 10 to the minus 19th joules. Now, it's convenient in high-energy physics to represent mass as energy over c squared, view of the relativistic relationship between mass and energy, E equals mc squared. So the mass of a proton in those units is just under 1 billion volts over c squared, or electron volts over c squared, or 938 MeV over c squared. Of an electron, it's about a half an MeV over c squared, or 511 kilovolts over c squared. Okay, so much for the background. Now, little history. In 1912, radioactivity in X-rays had been discovered. A detector technology in those days was an electroscope. And in fact, let me give you a little example of an electroscope. The point is, here is a little pivot rod, and it's very nearly perfectly balanced, and so it takes very little force to hold it out. Now, if the rod and this piece here have the same electric charge, and they're electrically connected at the pivot, then the electric charge, the mutual or same charges repel, and so this thing will be pushed away. So I have here a little generator, and I'll go sing. It's here. There. Okay, see, so it stands away. And if I discharge this, electric charge would leak through my finger. Okay, goes back. Now, could we set up that gadget over there? This is an electroscope that is on a projector, and there is a radioactive source. Now, if I put a radioactive source first we charge it up, and there it goes way over. But if we then put a radioactive source there, the radioactive source produces, the charged particles racing through the air ionize the air. And the ionized air is electrically conducting. And so the radioactive source causes the ions, causes the charge to leak off of the electroscope, and the vane of the electroscope will collapse. So I put on the source, and whoops, and now over time, you can see that thing leak off. Okay, go slowly, but okay, there you are. Now, Victor Hess knew about electroscopes, and he found that as you went up in elevation, an electroscope discharged more rapidly than just down here at sea level. Although even at sea level, it's slowly discharged, even without introducing any obvious radioactive source. And in fact, he took an electroscope up in a balloon and found that indeed in a balloon, the thing discharged even faster. And that led him to the conclusion that there was radiation coming from outer space, incident on the Earth's atmosphere, and in the atmosphere absorbed some of it, so that by the time we were down at sea level, under the depth of the Earth's atmosphere, there was much less. So he concluded that there was this radiation, and that was, in fact, what were called cosmic rays. It's just the same thing I've been saying. He is the discoverer of cosmic rays, or he's given that credit. Okay. Now, at that time in the 1912, 1920s, it was thought that the cosmic rays were really X-rays or gamma rays. It wasn't until the 1930s that it was learned that cosmic rays are indeed particles. It is now understood that primary cosmic rays are indeed atomic nuclei, protons, alpha particles, and indeed heavier nuclei up to and elements including iron. Heavier nuclei are also there, but much less common. Neutrinos are also incident on the Earth and may be called cosmic rays, and sometimes very, very energetic gamma rays, trillions of volt gamma rays, are included in cosmic rays. Okay, it's probably worth spending a few minutes talking about detectors. Geiger counters, earliest 20th century electronic counters, typically they were cylindrical tubes with a wire in the middle, then filled with gas, a high voltage on the central wire, and when a cosmic ray particle went through, an ionizing particle, gas was ionized, the gas became electrically conducting, and an electric current pulse popped across between the cylinder and the anode wire, and you got an electrical signal. Okay, cloud chambers came in the 1930s and through the 1950s, and we have a cloud chamber here that Warren Smith has provided for us. And here the idea is that you have a gas which has a vapor in it of water or liquid, and this gas is, or the vapor is at a super unstable state, so that some disturbance will cause the vapor to condense into droplets. And what would cause the vapor to condense into droplets? Well, ionization, and a high energy charged particle going through the vapor leaves a trail of charged gas ions, and they form condensation nuclei for water droplets. So you see these chains of water droplets, and that's what forms these trails, these tracks, is a radioactive source in here of alpha particles. And so this technology became a very, very widespread and valuable technology for studying cosmic rays in the 1930s through the 50s. Now, scintillation counters are very nice gadgets also. The point is, certain plastics with certain chemicals dissolved in them give off light, ultraviolet or purple light, when a charged particle passes through them. And that little flash of light can be detected by a photomultiplier. Now we have a photomultiplier here. This is just a very little 2-inch diameter thing. The point is that one end of it, this is the photocathode. When light strikes that, electrons are given off, and they go into they're focused into this structure, and they strike a piece of metal, and more electrons are kicked out of the metal by one electron hitting it. So you get electron multiplication, and a cascade of about 10 of these different electrodes give you a pulse, which is electrically easily detected at the output end when just a single photon or two strike the cathode. So these scintillation counters, using plastic and then viewed by photomultipliers, are very useful and practical cosmic ray devices. We have some over here, wrapped up in black paper and tape, black tape, are scintillator slabs, and at each side is a photomultiplier looking through a tapered piece of plastic. And there's one here and one here. A cosmic ray, which passes through this and this, gives a pulse in each, and the electronics detects when the two pulses are in time coincidence and tells you that there has been a cosmic ray passing through. And the little ticks you hear here are due to cosmic rays. Now, in a few minutes, I'll tell you what those cosmic rays are, but okay. On the detector discussion, okay. Well, I should also note here that besides the scintillation counters, another phenomenon which is relevant for detecting cosmic rays is Cherenkov radiation. If a charged particle passes through a substance where the velocity of light in that substance is lower than the velocity of the particle, what you do is you generate this so-called Cherenkov radiation. The simple analogy with which you're all familiar is a boat. If you have a boat going slowly through the water, okay, you have little ripples and so on. But if the boat is speeding, if it's a speedboat, you're all familiar with the fact that there is a wave that comes from the bow of the boat. And a V-shaped wave propagates away from the boat as the boat speeds along. We call it a bow shock. And exactly this, an analogous phenomenon is the production of radiation by a charged particle going through a dielectric medium. So this light, discovered and named by a Russian scientist, Cherenkov, is called Cherenkov radiation. Now, in various liquids and plastics and glass, it's obvious that the index of refraction is 1 1/4, 1 1/2, something like that. So velocity of light is 2/3 or so 3/4 of what it is in vacuum. And so there's obviously Cherenkov radiation. Even air has a finite density, and the velocity of light in air is less than it is in vacuum. So, although it's much less intense, there is Cherenkov radiation produced by charged particles moving at essentially at the velocity of light through air. I should also note, and it isn't on my transparency, that nitrogen in particular, when charged particles pass through, does emit a small quantity of ultraviolet scintillation light, so that although it's not very useful in a small experiment, in some of the larger experiments, which we come to later, this is relevant. I should also note that silicon detectors and other more modern things are very relevant to cosmic ray experiments. Superconducting magnets, for example. So the cosmic ray technology makes use of the devices which are used throughout the rest of physics. Okay, next slide I'll show cosmic ray spectrum. And we're talking about a range of energies from 10 to the 9th to 10 to the 20th electron volts, and flux, which goes all the way. Now, this is kind of a confusing slide. In the first place, if you can't read it, the flux is in particles per square meter, per steradian, per second, per billion electron volts, or per GeV. And this runs from 10 to the 4th all the way down to 10 to the minus 28th. In other words, over 32 orders of magnitude. That's a long range. And in energies from 10 to the 9th electron volts, or a billion electron volts, up to 10 to the 20th electron volts. And this is the spectrum of cosmic rays, more or less as known. This dotted line is an approximate curve but the real spectrum actually deviates a little bit. There are two characteristics here. One is what's called the knee, a break in the spectrum at a couple times 10 to the 15th electron volts. And then there's another feature, a break in the spectrum called the ankle up here at about 10 to the 18th. Well, sometimes a more useful curve, is this one. This is an integral spectrum. That means for every point here, for example, that point, there are 10 to the minus fourth particles per square meter per second per steradian at and above this energy. Well, that's not a very high flux. But you get down here, and over on the right side, there's a flux per square kilometer per year per steradian. And at energies of the order of 10 to the 19th, that means there's only about 1 particle per square kilometer per year at and above 10 to the 19th electron volts. This wide width of this thing represents the uncertainty. In fact, there are some uncertainties here. Now, the two energy scales, down here is the energy scale we've just been dealing with, the energy of the cosmic rays. But on the top, if the cosmic rays are protons, and many of them are, when a proton strikes another proton, the energy available in the center of mass, that is the energy available to do something interesting and unusual, is very much less because so much energy goes to knocking the other proton forward. The center of mass energy in trillion electron volts goes from 0.1 to 100 at that line, while the energy of the cosmic ray goes from, 10 to the 12th to 10 to the 19th or so. So these are center of mass energies. Now, one reason for putting those there is that down here I have 4 bars which represent the center of mass energies made available in high energy accelerator colliding beam machines. Here's the intersecting storage rings at CERN, built in about 1965. Another collider at CERN, ASP-bar-PS, about 400 GeV in the center of mass. And the Tevatron collider at Fermilab in Illinois, which Myron Campbell's involved with, producing about 2 trillion volts in the center of mass, equivalent to about 2 times 10 to the 15th electron volt cosmic ray. And here is the Large Hadron Collider nearing completion at the CERN laboratory in Geneva, Switzerland, which will produce an energy equivalent to a cosmic ray of about 10 to the 17th electron volts, that is 14 trillion electron volts in the center of mass. Now, somebody was pointing out to me, and I've heard this discussion before, that some people in Europe are upset about the Large Hadron Collider. They say, my gosh, suppose producing these particles, this tremendous amount of energy gives us a big surprise. Suppose it produces black holes that wind up swallowing up the Earth. My gosh, what are we going to do? And in fact, somebody's brought a lawsuit against the CERN organization. Well, the answer to that is very simple. The Earth has been bombarded for its existence by cosmic rays with much more energy than the Large Hadron Collider will provide. So don't worry about that, but you might wonder what might happen if a cosmic ray hits you. Okay. Anyhow, okay, let's talk about low energy cosmic rays. This is the range of energies where the flux is low enough so it can be studied directly with balloon-borne or satellite-borne detectors above the atmosphere. And these can include magnetic spectrometers and so on. I list down at the bottom of that transparency a few of the particular devices that have been used, including AMS, which is the program that Professor Ting is involved in and mentioned in his talk 2 weeks ago. He originally called that the antimatter spectrometer, but NASA decided it was better to call it something that didn't include the word anti, so it's called the alpha magnetic spectrometer now. Okay, now generally agreed that the source of most of these primary cosmic rays in this energy region is shock wave acceleration associated with supernovas. That is, a supernova is a star which has burned down to a point where it then explodes dramatically. And the technology is explained by the experts. I won't take time to go into it here. But there is very good reason to believe that this is the source of these cosmic rays. The composition of the cosmic rays is somewhat similar to the composition we know to be the composition of stars and other matter in our galaxy and the universe, that known spectroscopically, and of course the cosmic rays are identified in these cosmic ray events. Here's a graph at energies of billions of volts of the relative abundances of elements in stars, which are the black circles connected by the dotted line, and the abundance, relative abundance of cosmic ray nuclei, open circles connected by the solid line. Now, in many of the elements, the compositions are similar. In fact, I think the graphs were normalized to silicon, for example. And the interesting point is that some of these nuclei in our stellar compositions are very, very much less abundant than they are in cosmic rays. This is well understood now as the consequence of some of the more abundant nuclei, like carbon and oxygen, neon, for example, experiencing collisions with the residual gas and dust in interstellar space in our galaxy and undergoing a nuclear breakup, so that if a few nucleons are knocked out of our carbon nucleus, it becomes a boron or beryllium or perhaps a lithium nucleus. Which means that they're much more abundant in cosmic rays than they are in the stellar atmosphere. And so this is relatively understood, relatively well understood. The next slide, well, these are the energies per nucleon of iron, carbon, helium, and hydrogen in cosmic rays, up to a few billion electron volts per nucleon. Okay, now just to show you what is happening, here is an Italian satellite-borne detector, which was launched last year, and I don't know any of the physics results from it yet, but again, here's a magnet. The particle momentum can be determined by tracking the particle through the magnet, detectors above, and a so-called calorimeter to measure the total energy of a hadronic particle or nucleus below. Now, an interesting aside is the issue of antimatter. And again, Professor Ting touched on this a couple of weeks ago, and it is interesting. The apparent asymmetry of the universe, the lack of primordial antimatter, remains an unresolved mystery. The standard model of particle physics suggests that the Big Bang origin of the universe should have resulted in as much antimatter as matter. Why we have a matter-dominated universe is a mystery. Is it perhaps due to CP, non-conservation? Well, if there were antimatter galaxies or galactic clusters, antibaryonic cosmic rays from them might well diffuse to the vicinity of our galaxy. However, for billion, trillion volt energies, the local galactic magnetic field, our galaxy along the spiral arms has a magnetic field of the order of a microgauss, would actually contains the cosmic ray nuclei for literally millions of years. The age of the cosmic rays in the billion, trillion volt range has been determined by the isotope beryllium-10, which is radioactive, with a lifetime of the order of 1,000,000 years. And so by looking at the abundance of beryllium-10 to other isotopes in that range, we can get a measure of the age of the cosmic rays. And this leads to the conclusion that these cosmic rays they've been around for a long time at these energies. Now, therefore, because the galaxy acts like a bottle containing the cosmic rays, it is correspondingly difficult for an extragalactic cosmic ray of those energies to come into the field. And so it may be necessary to have sensitivities the order of 1 particle in 10 to the 10th to detect these extragalactic cosmic rays. Nevertheless, the Antimatter Spectrometer Program, or the Alpha Magnetic Spectrometer Program, would like to do this and would like to put their instrument on the International Space Station. Well, they're having big funding troubles with NASA. NASA currently has put its emphasis on putting people on Mars and so on. So there's a big problem. But okay, Ting is a good politician. We'll see. This is Ting's detector he used on a space shuttle experiment a couple of years ago and produced some very nice physics. So it is going forward. Okay, now antiprotons are not what you want to look for. You want to look for anti-carbon or anti-helium. The point is that we know if we have a high-energy accelerator that a proton striking another nucleus will make occasionally an antiproton. And so we do see antiprotons in these experiments. The dotted lines are those calculated, knowing the age of the cosmic rays in the galaxy and the spectrum. And these various points are from a whole mess of different experiments, including the 2002 AMS experiment. And we see that, in fact, there's about 1 in 1,000,000 to 1 in 10,000 antiprotons per proton over these energies up to billions of volts. Okay, well, end of the antiproton thing. Let's go on to higher energies. Between up to above 300, 500 trillion volts, the flux is too low to be studied by satellites and balloons. And so we have to use ground level observations. Now, the energetic cosmic rays entering the atmosphere initiate what are called air showers, which produce a rain of particles which can be detected on the Earth's surface, with detectors spread over a broad area. So we'll talk about these intermediate energies, 300 TeV to 100 PeV or so. Okay, when a primary cosmic ray enters the atmosphere, it has a collision with an air nucleus and produces pi mesons, nucleons, protons and neutrons, occasionally heavier hadrons, which rain forward, mostly produced forward because the momentum of the incident particle. The charged pi mesons decay to a mu meson and a neutrino. The neutral pi mesons decay promptly into 2 gamma rays. Some fraction of the pions, of course, have a nuclear interaction before they decay, producing, in fact, more pions. And the gammas produce electron-positron pairs, which produce more gammas by bremsstrahlung. The resulting electromagnetic cascade produces a rain of electrons and gamma rays on the Earth's surface, and also muons and some hadrons. This is a schematic diagram of an air shower. See, the primary cosmic ray hits the top of the atmosphere. Over here are the gammas and electrons separated, not because they're separated in space, but just graphically so you can identify them. In the right hand are the pions decaying to muons, and the muons, since they are weakly interacting particles, to be sure lose some energy by ionization, but mostly reach the Earth's surface, unless they are slow enough energy to decay into electrons and neutrinos before they reach the Earth. And then some of the nucleons, protons and neutrons, eventually reach the Earth's surface, although their cross-section is high enough so most of them have dissipated by the time they get to the Earth. Well, this is a graph, for example, for an incident energy of 10 to the 15th, or 1 PeV, 10 to the 15th electron volts. Here is the depth in the atmosphere in grams per square centimeter. You know, the atmosphere is about 1,000 grams per square centimeter. That means above 1 square centimeter of atmosphere, the column of air weighs a kilogram, or in more familiar terms, perhaps above a square inch, the column of air to the top of the atmosphere weighs 14.7 pounds. Okay, well, here is the altitude in kilometers. So 3 kilometers is about 10,000 feet, for example. So these are mountain elevations here. Okay, here are the number of electrons produced on the average as a function of height in the atmosphere. For proton primaries, that's this curve, and for iron primaries, this curve. The iron primaries produce more electrons early on, and then they are attenuated and fall away more rapidly than that from protons. At the same time, if you measure the mu mesons from proton and iron primaries, this is as a function of depth in the atmosphere. So as you see, if we're sitting near the Earth's surface, measure electrons and mu mesons, the higher the ratio of mu mesons to electrons, the more probable it is that the primary is a heavy nucleus. Then lower ratio of muons to electrons are probably protons or lighter nuclei. Now, the fact that these muons are penetrating particles, they've gone through the atmosphere, they even go through the roof of buildings. And that's the point of this little demonstration here. What we're seeing here are mu mesons from cosmic rays which interacted high in the atmosphere, passing through these 2 scintillator slabs. And these 2 slabs are in coincidence, which means we only get a count and make a tick when a particle goes through this and this within a time interval of a fraction of a microsecond of each other. And we, if you want to put it this way, if we go outdoors at this elevation, close to sea level, per square centimeter, we are experiencing about 1 cosmic ray per minute. And if you have counters and detectors, that can be seen. Now, if you go high in the atmosphere, you detect primary cosmic rays. One detector technology I did not mention are nuclear emulsions. As you know, of course, if you strike a particular substance inside a photographic film with light, it separates the silver nucleus from the rest of the molecule. And so when you develop it, you get little granules of silver, which cause you to see a film. Now, a charged particle going through nuclear emulsion has the same effect. That is, a charged particle will leave a trail of little silver granules, which when the film is developed, you can then see as a track. Now, what the cosmic ray people have done is build very, very large blocks, slabs of nuclear emulsion, which are millimeters thick, and they stack these together and then expose them, for example, in a high-altitude balloon, and then develop them. Well, I didn't put this on a transparency, but this was given me by a British cosmic ray physicist. This is a nuclear emulsion reconstruction, and there are many, many pieces of emulsion here that have been put together to show this. This is an incident primary iron nucleus with an energy of the order of 20 trillion electron volts. And his calculation, his reading of this, is that there were about 750 mesons produced. And you see all these tracks. Here's the incident iron nucleus. Of course, iron has an electric charge of the order of 28 times that of a proton, so the ionization is very significant there. Here's a collision, and most of the particles go forward, but you see tracks coming out in every direction, and these have all been developed. So this historically was a useful and valuable technology in cosmic rays. Okay. Well, let's go ahead. This is the overall cosmic ray spectrum through this, primarily the intermediate energy region from about here to here. These are data from direct observations, and then up here things are a little more confusing. Okay, and again, the point of this is that, again, the scale here is multiplied by energy cubed, so where the curve is relatively horizontal, it means that the energy of the spectrum is falling as energy cubed. The energy spectrum is falling less rapidly here, which is why the curve is going up, and then here is this so-called knee I was discussing. Okay. Now, a major problem in this energy region is the interpretation of the ground level data. It depends on understanding the primary interaction, and data from these energies are not yet available from accelerators. We hope that the Large Hadron Collider at CERN will provide some. This impacts the understanding of the elemental composition more than the energy. It appears that the primary composition is becoming heavier through this knee region. This is from Jim Matthews' talk a couple of years ago. What is plotted here is the average of the natural logarithm of the mass number. If it were pure hydrogen, the log of the mass number 1 is 0. If it were pure iron, the natural log of 56 is about 4. So what is clear is that there is a mix of nuclei present, and in fact these points down here are from direct observations, but there is very significant confusion in understanding the mass composition of cosmic rays in this energy. These are from two different kinds of observation. These are from ground level measurements. These are from measurements using optical devices, that is air Cherenkov radiation and air scintillation. And the point is, there's a lot we don't know. Well, it would be inappropriate not to note here that during the 30s and 40s, a lot of new elementary particles were discovered in cosmic rays. Positrons, mu mesons, pi mesons, kaons, in fact, particles containing the strange quark, hyperons, and so on. In fact, when the first multi-billion volt accelerator was completed at Brookhaven in 1952, it was called the Cosmotron. And, well, okay, because it was able to mimic the cosmic ray discoveries, in effect. Okay, what is responsible for the break in spectrum of the knee? Well, for one thing, it's probably the upper limit of this supernova shock acceleration. Another is that it's, from reasonable calculation, an upper limit to the galactic confinement of cosmic rays. That is, this 1 microgauss in the 100 kiloparsecs scale of the galactic arms is about, well, it's called the leaky box model. It's not very effective in containing particles above a few times 10 to the 15th electron volts. In either case, heavier nuclei would be accelerated and contained in the galaxy to higher energies than lighter nuclei, which would explain why the average mass composition increases. Still, displays of existing data show vast uncertainties. It is appropriate to note here, since we're at the University of Michigan, that one of our faculty members, Yukio Tomozawa, has a theory that there may be a very massive neutral particle with a mass of the order of a PeV, 10 to the 15th electron volts, which is a major source of cosmic rays and which is responsible for the knee. To be sure, his theory is still unproven, but worth noting. Okay, let's talk about the highest energy cosmic rays in the last few minutes. Great interest in the high energy cosmic rays over the range between 10 to the 17th and 10 to the 20th electron volts. Note that a 10 to the 20th electron volt cosmic ray is equivalent to 16 joules approximately. That is equivalent to a 1 kilogram mass. I should have asked Warren for a 1 kilogram mass, dropped from about 5 feet. That this just a fundamental particle, probably a proton, has that energy. That's pretty remarkable. But to understand the spectrum and so forth, very large detector arrays must be used, and it's used in view of the very small flux, particles per square kilometer per year. A most notable recent program to study these extreme energies is the Pierre Auger Observatory in Argentina. Pierre Auger was a French physicist who, in the late 1930s, first discovered extensive air showers. Okay, now I'm going to use transparencies that were given me by Jim Matthews, who's a member of this Pierre Auger collaboration, was on our staff here at Michigan for many years, is now a full professor at University of Louisiana. Okay, and here's just a recall of some of the energy scale. 10 to the 21st electron volts, 1 ZeV is 160 joules. And for trying to think of a name to call these things, that energy scale, you could call it a Tyson or a Clemens or a Harry or a Curly. Okay. Well, here's the location of the Pierre Auger Observatory. They want to build one also in North America, probably western Colorado, but currently they have support from Argentina and have this facility in Argentina. This is an aerial view of the place where the array is, and I think that is roughly, I don't know. Anyhow, this is a flat area where the Santiago, Chile is over there. I think this is a satellite view. It's from a big distance. Okay, this is a diagram of the way the thing works. What they have are these, in blue here, these containers which are basically containing purified water, and on top they have photomultipliers which detect the Cherenkov radiation of the electrons and the mu mesons coming through the tanks. And here's a man, so you get a picture, a feeling for the scale of this thing, something like 10 or 12 feet in diameter and 4 or 5 feet high. And the little panels here are solar panels, so each of these things is independently powered. and the data is broadcast using basically cell phone technology to a central station. And then they have these telescope arrays to look at the atmospheric scintillation light produced by the cosmic ray air shower along the way. And this is, again, a diagrammatic representation of an air shower. Here, another view showing both detector systems. Here are two rays of telescopes, so they get a stereoscopic picture of the cascade. And here, an array of the ground detectors, and from the relative timing of the incidence of the particles on these detectors, they get a measure of the direction from which the air shower is falling. And in fact, this disk diagrammatically represents the fact that all these particles traveling at the speed of light arrive at the ground within a meter or two of each other in longitudinal position, or a fraction of a very small fraction of a microsecond. But of course, over a distance laterally of a kilometer or more, there is adequate time difference to get the direction. Now, this is a little diagram again of a cascade of particles. And if I had a fancier projector, this thing actually moves in time, but I don't, so we'll skip that. Okay, and this is the array. Now, these detectors, here's a map, are deployed at a spacing of 1.5 kilometers. There are about 1,600 detectors, and the area of this whole array then is about 3,000 square kilometers. So that's necessary to get adequate data in a finite number of years with up to energies over 10 to the 20th electron volts. And then these telescopes looking at the fluorescent light from the air showers are located at these 4 locations. Each container, each little housing contains 6 telescopes. And incidentally, a problem, the telescope arrays looking at the air scintillation are only useful on a dark night. So bright moonlight night or a cloudy night, you can't get data there. The surface detectors, of course, work all the time. But the average useful fraction of the time of the atmospheric fluorescence detectors is only about 5%. This is a photograph of one of the surface detectors, and here a couple of guys working on one, so you get to measure the scale. Of course, this is in a field where the cattle graze, and they don't bother the cosmic rays, and cosmic rays don't bother them. This is the atmospheric fluorescence telescope array. Here inside is one of them. There is a spherical mirror, a corrector lens, and then this array of 440 photomultipliers, like this one that we looked at earlier. And this is what is used to look at the atmospheric fluorescence. Okay, this work was featured on the covers of Science magazine a few weeks ago, and the critical outcome was the following. Each little circle or ellipse represents one incident cosmic ray, its direction, where the energy was at least about 6 times 10 to the 19th electron volts, whopping energy. And each little X here represents an astronomical object called an AGN, or an active galactic nucleus. Most of the cosmic rays in this energy range are coincident within the resolution of the instrument of an active galactic nuclei, an active galactic nucleus called an AGN. So the current understanding, and of course data continues to be collected, is that the very highest energy cosmic rays come to us from AGNs. Now, I should note that we talked about the bending of cosmic rays in the magnetic field of our galaxy. There is a magnetic field outside the galaxy, but it's very small. I mean, we talk about a microgauss in the galaxy. It's presumably a hundredth or a thousandth of that outside the galaxy. And the fact is that with the cosmic rays of 10 to the 19th, 10 to the 20th electron volts, the charge of a proton or of a heavier nucleus, they would not be deflected significantly over the path distance of hundreds, thousands of light years, million light years. So they do represent the direction. Now, just mention briefly that there is calculated to be a cutoff of the cosmic ray spectrum due to the interaction of the high energy, very high energy cosmic rays above 30 eeV, or 310 to the 19th, with the 2.7 degree Kelvin microwave blackbody radiation. That is, above this energy, they would produce pi mesons in interacting with the blackbody radiation, and this would attenuate the flux. So you'd expect a fall off in intensity at those energies. Well, the spectrum does show a fall off above about 19.5 log, well, 10 to the 19.5 eeV, or electron volts. And this shows it a little more explicitly. Okay. So the summary of the Auger project: AGNs are a priori good candidates, and I won't go through a lot of this. At the energy spectrum, the GZK steepening does seem to be there, the anisotropy regardless of the assumed sources, and so on. So let me summarize, and I think I've exhausted my time, what we have discussed. We've discussed more details of other experiments, but there isn't time. The overall conclusions, what we know so far and what we don't, have been covered. We still don't know the composition above a PeV very well, don't really understand the sources through the whole energy range as well as we would like. Early cosmic ray physicists discovered many new particles, and Russian and Japanese physicists in particular continue to claim new phenomenon. But I think we'll close here. I had a couple comments on radiation danger in space and so on, but I think we've run out of time, so I think we'll stop there. Thank you very much.
Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program.